This video serves to illustrate the paper Mouse and Keyboard Cursor Warping to Accelerate and Reduce the Effort of Routine HCI Input Tasks. In this work, we show how using gaze information can speed up and reduce the muscle strain associated with common input tasks during human-computer interaction. Specifically, we show how a large part of the manual movement required to reposition a mouse or keyboard cursor can be eliminated by warping the cursor towards the user point of regard on the screen as estimated using gaze estimation algorithms. The method combines both manual input from the user to indicate intent and final fine-grained positioning of the cursor and an attentive user interface that adapts the cursor position dynamically according to the user manual input and gaze position on the screen. We have studied 4 common tasks carried out during human-computer interaction: target acquisition, text cursor repositioning to text selection, and a drag-and-drop operation. Let's look now how cursor warping can speed up and reduce the muscular strain associated to common input tasks during human-computer interaction. For the mouse cursor warping experiment, the subject is first required to click at a random target on the screen for 10 trials. For each trial, both the target and the mouse cursor appear at a random position on the screen. So the subject simply has to click at the random target for 10 trials. Mouse cursor warping consists of making the mouse cursor jump to the area of the screen where the user's gaze is estimated to be placed whenever a slight mouse movement is detected and proven that the mouse has been quiet or stationary for a few seconds. So for example, we see that the mouse cursor in this screen is situated at the center left of the screen. If the user looks at the click me target and then moves the mouse slightly, the mouse will jump to the gaze estimation area, and then the user just completes the clicking on the target by manually moving the mouse. To better visualize what is happening in this experiment, we have generated a red dot that moves around the screen and which indicates the user gaze coordinates as estimated by the gaze tracking algorithms. So at this moment in time, I'm looking at the center of the screen, and mouse cursor warping consists on the fact that the mouse cursor is in this area of the screen, and whenever I look at the target that I have to click, if I move the mouse slightly, the mouse cursor jumps to wherever I am looking at, and then I complete the selection by clicking on the target. To minimize overshooting of the mouse cursor when placed over the target according to the gaze estimation area, an inertia compensation mechanism can be put in place by which, instead of placing the cursor at the center of the gaze estimation area, the cursor position can be offset towards the incoming path of the manual mouse actuation vector. This technique increases the time required to perform target acquisition, but makes the cursor appear in motion toward the target after the warping occurs, which some users find convenient. Some of the most impressive results of using the warping concept and gaze tracking technology to speed up human-computer interaction were obtained in the text cursor warping experiments. In these experiments, the users or the subjects were requested to place a keyboard text cursor within the boundaries of a word highlighted in red. In the control experiment, the word appeared at a random position for 10 trials, and the text cursor was also placed at a random position. Subjects were requested to position the text keyboard cursor within the red word, both first using the keyboard and in another experiment using the mouse. So just by using the direction keys or any combination of control keys plus direction keys, the text cursor was carried to within the highlighted word, and at this time the timing watch was stopped. Then the subjects move to the next trial by pressing F1, and there's a new word highlighted in red, and the text cursor has been placed at a random position, so the user just has to bring the mouse cursor to within the word, and do that for 10 trials. Using text cursor warping consists on moving the keyboard text cursor to the area of the screen where the user is gazing at, which for this task would be around the word highlighted in red, and whenever a direction key is detected to be pressed, making the text cursor jump towards the highlighted word. So for example, here we see that the text cursor is in the word alignment. The target to which we have to bring the text cursor is here, and if we look at it and press any direction key, the keyboard cursor jumps to the vicinity of the word, and then we complete the selection manually using the keyboard key. We do it for another interaction. Task here is the text cursor, and we jump the text cursor towards the target word just by pressing only a few times the direction keys. Here is the text cursor, here is the highlighted word. We look at it, we press a few times the direction keys, and the cursor jumps to the vicinity of the word. Again, using the visualization of the gaze estimation area helps a lot to illustrate the concept. So at this moment, my gaze is looking at the vicinity of where the text cursor is, and if I look at the target word and I click a direction key, the text cursor is bring within the vicinity of the word, and then I complete the task manually. Let's do it for a few times. Here is the random position in which the text cursor has been placed. Here is the target word, and I move towards it in just 3 keystrokes. Again, here is the text cursor, the target word, and I quickly move to it. For the text selection experiment, 2 words appear highlighted on the screen, one in blue, one in red. The idea is to select all the text between both words and starting always the selection from the blue word. So the idea is like the cursor again appears in a random position, and we bring the cursor towards the blue word and we initiate the selection and completed it all the way to the red word, and then we press F5 to stop the time watch and to finalize the counting of the keystrokes required to complete the task. Using cursor warping to complete this task consists on first looking at the blue work, then initiating the selection and looking at the red work, and both times the cursor should jump to the vicinity of where the person is looking at. So we look at the blue work and we press any direction key and the cursor jumps to the vicinity of the work, and then we initiate the selection by press and holding the shift key and look at the red work, and then the selection should jump to the vicinity where we only have to do a few keystrokes to complete the selection. Once again, the mouse cursor is at a random position here, and we look at the blue work and press any direction key. The text cursor jumps to the vicinity of the work. We initiate the selection by press and holding the shift key. We look at the red work and the selection is almost completed. Once again, showing the visualization of the user's gaze helps a lot to illustrate the concept. So for example, I'm looking now at the random position where the text cursor is located. I look at the blue work, the text cursor jumps to the vicinity of the work, and then I look at the red work and I press and hold shift, press any direction key, and the selection is almost completed. For the drag and drop experiment, the idea is to drag the gray target into the blue target using a traditional drag and drop operation. For each interaction or trial, the mouse cursor and both targets appear in random positions. The process for performing a drag and drop operation using cursor warping is a bit more elaborate, and probably it has a step learning curve. The idea is to look at the first target, the gray target, and then move the mouse slightly. By doing this, the cursor jumps to the vicinity of the button. Then we press and hold the left button of the mouse and look at the blue target and move the mouse slightly again towards the blue target, and by using the gaze estimation information, the cursor jumps to the vicinity or within the blue target. Here also, visualization of the gaze estimation information probably helps to illustrate what the subject is required to do and what is going on behind the scenes. So the mouse cursor appears in a random position, and the task to be completed is to drag and drop the gray target towards the blue target. So the subject looks at the gray target, moves the mouse slightly, and the mouse cursor warps towards the vicinity or within the gray target. Then the subject needs to press the left mouse button and hold it, then look at the blue target, move the mouse slightly, and the mouse warps within the blue box. We do that for several times, and it will immediately become clear how the whole process works. As you can see, the process can be very fast, but it can be confusing for the users at the beginning, and it requires time to practice and to improve the performance, unlike the other tasks where users adapt quite quickly to this new interaction modality. In order to further investigate cursor warping, we have also carried out experiments to test the performance of cursor warping across monitors in multi-monitor desktop scenarios. In such scenarios, mouse movement amplitudes to acquire targets across the entire desktop can be particularly large and inconvenient for users. Cursor warping across monitors requires the usage of several eye trackers and a robust algorithm to estimate head orientation to determine the monitor where gaze is being placed. First, each eye tracker is calibrated in order to generate a gaze model specific to a head pose used to gaze at a given monitor. Using two eye trackers, cursor warping can then be used to acquire targets across both monitors in a seamless manner. Again, for visualization purposes, we use a red disk to represent gaze that is not supposed to be present in real scenarios. Here, however, it helps to illustrate how cursor warping operates. So in summary, cursor warping is an important tool in the creation of attentive user interfaces that adapt dynamically to the information coming both from the hands and the eyes to speed up human-computer interaction and to reduce the amount of effort required in common repetitive input tasks. With this, I conclude this demonstration video. I hope that you have found the concept of mouse and keyboard cursor warping interesting.